In this video, we're going to be formalizing some of the work that we've already done by conducting what's called a z-test, which is a common hypothesis test that we do usually when working with proportions. But we're going to be doing kind of the same thing that we've already done, just using this formal notation and talking about why we're doing the steps that we do. So first off, we're using this context with support for the current governor. We asked people how likely they were if they would vote for the governor again if he was or she was against a similar challenger. The null hypothesis is that it would be the same, that the governor has the same support, which is 55.1%. Our p-hat, our sample proportion, was 58.2%, suggesting that in our sample, slightly more people said that they would vote. But is that just sampling variability? Is that just because we asked 500 people and we're going to get a little bit of variability around that 55.1%? Or is this difference indicative of a true movement in the population, that the governor is more popular than before? So what we're going to do is take our p-hat, and we want to calculate the standard error of p-hat. In other words, we want to know, based on this information, if support really is 55.1%, how much error should we expect in our sample statistic, in our sample p-value, in our p-hat value, I should say, if we sampled 500 people here. So I'm going to do the standard error of p-hat, as you might remember, is going to be sigma over the square root of n. Now, since we're using a null hypothesized p, a null hypothesized proportion, we can calculate the null hypothesized sigma value to be 0.497, which we would get if we use the standard deviation formula or something like that to get this value. We're not, at this point, we're less concerned about calculating sigma by hand in the context of proportions and more just kind of moving on and learning the methods and using software like R to do some of this calculation for us. So we're just going to kind of provide this value from here on and calculate some of this by hand and think about what it means. So the standard error for p-hat is going to be 0.497 over the square root of 500, which is going to come out to, let's see, 0.497 divided by the square root of 500. And I get 0.02226, etc. So I'm going to just say it's 0.022, and that's good enough for me. Again, software does the hard work for us. We're just kind of going through the steps to familiarize ourselves with the method itself. Okay. So that's certainly helpful, that we would typically expect about 2.2% difference, 2.2% error in our p-hat, given that we sampled this much. It looks like our discrepancy is a little bit more because we observed, I think it's about 0.031, about 3.1% difference. So what we want to do is kind of calculate how many standard errors off we are compared to, again, what we should be off, which would be the standard error. So what we're going to do is we're going to standardize this value, and we're going to call it z, which I will explain in just a second. But we're just going to find this discrepancy between 582 and 551, and we're going to divide it by the standard error value of 0.022. And what this is doing is it's going to tell us how many standard errors off our p-hat is from this null hypothesized p. And this is going to give us 1.409. So we are about 1.409 standard errors above this null hypothesized p. Now you might be wondering, why are we calling this z? Why is this called a z-test? And it has to do with what's called a standard normal curve, which I think we've talked about before, but I'll just kind of remind you that that the p-hats are normally distributed around p with a standard deviation of the standard error. So the standard error is the standard deviation of our sampling distribution here. And so what we're doing is we're just converting this to a standard normal curve. So to say, to recognize this discrepancy right here doesn't really mean much unless we know what the standard error is. So what we're doing is we're converting this to a value that we could calculate in any context with any units. So anytime we do a hypothesis test, we can standardize this discrepancy by finding the difference, dividing by the standard error to say that we are 1.409 or whatever standard errors away from the null hypothesis. And so what we're going to use is the standard normal curve to think about this. That the standard normal curve is centered at 0 with a standard deviation of 1. So this would be like 1, this is like -1, this is like 2, this is like -2. And we are at 1.409, so somewhere right around here. So this gives us a sense of how far away we are from this null hypothesized parameter. And we, again, by converting it to a z-score like this, we can kind of standardize this process every time we do a hypothesis test, and we can calculate the p-value associated with being at a z-score of 1.409 or higher, or of a discrepancy of 1.409 or larger in either direction. So this is where p-values come in. The p-value is the probability of being in that tail area. So we're way over here. So what I'm going to do first is I'm going to draw with I'm going to go back to blue for a second. So our distribution of possible p-hats is centered at 0.551 if the null hypothesis is true, with a standard deviation of 0.022. So this would be about 573. This is about another 2 standard deviations would be about 0.595, etc. And we can go the other way as well if we wanted to. And we can kind of draw this z-scale underneath if we wanted to. So this is the same as a z-scale or a z-value of 0, 1, 2. Sorry that my tick marks are not perfectly equally apart. They're approximate there. And so we're at 0.582 for our p-hat, which corresponds to a z-value of about 1.4, we said. And we can calculate the p-value. We can calculate this probability of being this far or farther away. Since we're doing a two-sided test, we didn't specify that we are interested equally in being this far above or this far below 55.1%. We're just curious if there's evidence of a difference. So we're actually going to do a two-sided p-value and calculate the tail probability on this side as well, that same distance away. Again, I feel like they're not quite symmetrical. It bothers me when they're not quite the same, but they're supposed to be the same. And actually, I don't know why I have 1.395 in here when apparently it is. It might just be a rounding thing where, maybe I did some rounding along the way because I got 1.409 here. But this number should be the same. So I'm not quite sure what happened there. So we can calculate with p norm, what happens if we are at 1.409 or higher with a mean of 0 and a standard deviation of 1, so using the standard normal curve, and a lower tail of false. That would give us a tail probability of about 8.15%. So since my approximation here is a little bit off, it's probably a little bit lower than that. But it's close enough. It's around 8%, I'm sure. So that means that this is about 8%. And then if I double that and I calculate the tail probability on the other side, this would be another 8% since it's the same distance away, so that I get a two-sided p-value of around 16%. So the two-sided p-value is about 16%. Again, I'm kind of dropping the decimals because of this little correction here. It should be slightly lower than what I'm seeing here, so it's probably right about 8%, I would guess. So yeah, I could also do p-norm with 0.582 plugged in, with a mean of 0.551 and a standard deviation of 0.022. That would work exactly the same. So either way will work for us if we want to use the standard normal units or if we want to use the original units themselves. But the standard normal units are helpful because we can do that in any context, and we can calculate a z-value like this, a z-statistic that is uniformly conveying the same information in any hypothesis test context that we might be doing. Just another word about directional tests. So if we were only interested in the direction going one way, if it was only important or noteworthy if it's higher than this value, and if it's lower, then it doesn't matter. If it's lower, it's really the same to us as if it was equal. If that's the case, then we're only going to get that one-sided p-value. But if it's equally interesting in either direction, if either direction departure means something to us, then we're going to calculate that two-sided p-value. So making a conclusion, this is a little bit subjective, and we're going to talk about on the next page here. A p-value is just telling us the probability of getting a sample statistic as far away as we did if the null hypothesized parameter is true. But it can't really tell us what to do about it. So that's where we get into kind of these, what's called a significance level and interpreting the p-value to make a decision. But the p-value in itself can't tell us what to do. It's just conveying information about how plausible or not plausible the null hypothesis really is here. So in our case, if the proportion of continued support for the governor were really still 55.1%, then we'd get a sample proportion this far or farther about 16% of the time by random chance with a sample of this size. Now that doesn't mean the governor's support really is the same. It could be different, but we don't have a whole lot of evidence to say that for sure. It's still kind of in that realm of plausibility here that the governor support's the same, but if we got a lower p-value, if we saw more discrepancy, or if we saw the same discrepancy with a much larger sample, then maybe we'd be a little bit more confident to kind of conclude that with more confidence here. So with that in mind, let's talk about decision making. A lot of times when we do hypothesis testing, we might set what's called a significance level, and that is going to be the point at which we decide to reject the null hypothesis, or if we don't make it, we just simply fail to reject it. We just say it's could be true, it's plausible. So having a significance level can kind of add a little bit more objectivity to your decision making. And oftentimes we work with an alpha level of about 0.05, where alpha is this cutoff point. It's a significance level, meaning that if our p-value gets below that, so if it's below, say, 0.05, then we feel like that's enough evidence to reject. The 0.05 is like that 1 in 20 benchmark. So 1 in 20 times we're going to see a result this unusual. So for a lot of people, that is a low enough probability that we feel good about rejecting the null hypothesis when we get there. Now, alpha doesn't have to be 0.05. It could also be 0.01. I've also seen it 0.005 before. So oftentimes in, like, say, drug testing situations or other kind of high stakes change environments, maybe you want to be a little bit more stingy about how much evidence you want, that you don't want to make a change unless you're really confident, unless you have a really low p-value. So there might be contexts where you do it lower than this. There's other contexts where change is not a big deal, where you really just want to go with what's best, in which case maybe your alpha level is more like 5% or 10%, just some indication of improvement. So, maybe it's not a whole lot of evidence, but maybe it's some, something here, that 1 in 10, 1 in 20 range, that's enough evidence to make a change. So all that to say, when your p-value is below the significance level, we would reject the null hypothesis. When it's above, we simply fail to reject. Now, why don't we ever accept the null hypothesis, you might be wondering. So if our p-value is above the significance level, shouldn't we be accepting the null hypothesis? Do we conclude it's true? The answer is not necessarily, because, right, so we still saw over here 58.1% for the governor, or 58.2% support for the governor. That does not mean his support is definitely still the same, right? So it's still different than 55.1%. The question is, am I confident that it's not? How much indication is this of true change, or is it still possible it's 55.1%? So really all we're doing here is we're just saying, hey, this null hypothesis could still be the parameter. We can't say that it's not, but we're not necessarily concluding it's true either. It could still be different. We just don't have enough evidence to say so. So I definitely kind of think of the courtroom scene here, where the two possibilities are guilty and not guilty. That if we have enough evidence, we conclude guilt. If we don't have enough evidence, if the evidence wasn't convincing, we say not guilty. We don't really conclude innocence in a courtroom. We just say there wasn't enough of a case, there wasn't enough evidence to conclude guilt. So same thing with hypothesis testing. We really can't ever conclude a parameter is a certain value. We just say whether it's plausible or not. Something else I want to mention here, it's not in the notes, but just a very quick word about type 1 and type 2 error. When we reject the null hypothesis when it really is false, great. That is a true positive. We have done the right thing. If we fail to reject the null hypothesis when it really is true, again, great. We have done the right thing. But just be aware of these two different ways that we can make errors. We can make what's called a type 1 error if we reject the null hypothesis when it's true. Think of this as kind of like turning the alarm on when there's no fire or there's nothing wrong. It means that we have kind of waved our hands and said, hey, there's a departure. We think something is going on here, but there's actually nothing going on. And this is directly tied to the alpha level that you set. Your alpha level is your chance of a type 1 error when the null hypothesis is true. So the higher you set your alpha, the more likely you are to do this, the more likely you are to mistakenly reject your null hypothesis. So you don't want to set alpha too high because you don't want to be, was it Peter and the Wolf? You don't want to be crying wolf when there isn't really a wolf because you set your alpha too high. But then the opposite can be concerning as well, and that is when you can't reject the null hypothesis when it really is false. So that is when there's something wrong and the alarm isn't going off. And both of these things have problems of their own, and context kind of dictates which might be more concerning than the other. So like I said, in drug testing, maybe it's better to keep the status quo and not pick the better drug unless you have a whole lot of evidence. There might be other cases where not making change is also critically problematic as well. So type 1 and type 2 error can be problems in their own ways, where context kind of dictates where we set that alpha level and which of those two things we're more worried about. Okay. And then lastly in this video is the idea of scaled decision making with p-values. And this is super important, especially in our class. We'd like to get away from just rejecting and failing to reject, because this kind of trivializes the information we're getting. It turns it into a binary rather than the scaled meaning that the p-value provides to us. So this is kind of how the field has been moving in the last 10 years, is less about getting your p-value below 5% and more about just reporting your p-value as one more piece of information about what's going on. That there's many ways to talk about your results, not just a p-value, but as we'll talk about later, effect sizes or models or other information about your results. So for that reason, what we're going to do in this class mostly is we won't be using significance levels all the time to make decisions, but instead we're going to get a p-value and then we're going to interpret it in context, what it's telling us. So here are some guidelines, some slightly more nuanced interpretations of p-values than reject and fail to reject. So when our p-value is above 10%, we're typically going to say that we have weak evidence against the null hypothesis, or little to no evidence against the null hypothesis. When our p-value is about 5 to 10%, we're going to usually call that more mild evidence against the null, meaning that we have some suggestion of change, but it's not very strong evidence. It's still kind of in that 1 in 10 to 1 in 20 range. For p-values of 1 to 5%, we're often going to say that we have fairly strong evidence against the null, that this is a pretty unusual result by random chance. And when our p-value is below 1%, that is very strong evidence against the null. That is less than a 1 in 100 chance to happen if the null were true. So keep these in mind. We're going to be using them in questions like on the homework, just how do we kind of make sense of this context and give a more nuanced interpretation of our hypothesis test result.